In the last class, we discussed about the concept of pure bending and pure bending equation. In this class, we will know about the concept of section modulus Z. So, in any cross section, every cross section of a beam can be defined by one of its property called as section modulus. As the value of section modulus is more, it is more stronger. That is the meaning. So it is defined as Z is defined as the ratio of moment of inertia of the section above the neutral axis to the distance of the farthest fiber from the neutral axis. That is INA divided by Y max. Its unit is I is expressed in millimeter power 4, distance Y max is expressed in millimeters. Therefore, the unit of section modulus is millimeter cube. Now, from the pure bending equation, we have My is equal to F max by Y max. So, from this we can see that it is M is equal to I divided by Y max into F max. So, this I divided by Y max is nothing but Z. So, Z can also be defined as M divided by F max. That is, it is the ratio of moment of resistance of the section to the maximum bending stress. So, F max can be called as maximum bending moment, or it can be called as the maximum bending stress, or it can also be called as permissible bending stress. So these are the wordings: permissible bending stress, or it can also be called as allowable bending stress. So these are the wordings you should note down. They can give any of these words. So the ratio of moment of resistance of the particular section to the allowable bending stress is also called as section modulus. So section modulus can be defined in two ways: ratio of moment of inertia to distance of farthest fiber from neutral axis, or it is the ratio of moment of resistance of the section to the maximum bending stress. Now let us find the value of section modulus for some of the standard sections which are used as beams. So rectangular section. First one is rectangular section. So I will consider rectangular section of width B and depth D. So this is the diagram. Neutral axis passes through the centroid of the rectangular section, which is nothing but the geometrical center. Now the distance of farthest fiber is d by 2 here. Y max is d by 2 from the neutral axis. The distance is measured. Since it is symmetrical section, whether you measure above the neutral axis or below the neutral axis, your Y max is same, d by 2. And we know the formula for moment of inertia of rectangular section as BD cube by 12. So now therefore Z is BD cube by 12 divided by D by 2. It is BD square by 6. So section modulus of a rectangular section is BD square by 6. Now coming to a circular section of I have taken diameter as capital D. So moment of inertia is pi d power 4 by 64. So this formula you should be knowing. And Y max, distance of the farthest fiber from the neutral axis, is whether this side or this side, it is capital D by 2 only. Now if you substitute in the formula, Z is given by I by Y max, pi d power 4 by 64 by D by 2, which is nothing but pi d cube by 32. So even if you don't remember, you can easily get the formula for section modulus by knowing the values of I and Y max. Now third one is hollow rectangular section. So hollow rectangular section means a portion of the section is hollow. So bigger depth I have taken as capital D, the smaller depth, inner depth I have taken as small d, outer width I have taken as capital B, inner width I have taken as small b. So now the formula for moment of inertia here is similar to the rectangular section. Only thing is, for a hollow rectangular section, moment of friction inertia is given by moment of inertia of the bigger section, bigger rectangle minus moment of inertia of the smaller rectangle, which is nothing but this. And your distance of farthest fiber, here also it is d by 2 only. There is no change in that, capital D by 2. Whether you measure above the neutral axis or below the neutral axis, it is capital D by 2. So Y max is capital D by 2. So if you divide INA by this Y max, you are going to get this. So this is the section modulus of hollow rectangular section. Next, coming to hollow circular section. So here also similar to hollow rectangular section. So outer diameter I have taken as capital D, inner diameter small d, neutral axis passes through the centroid. Now moment of inertia is given by, for a circle it is pi d power 4 by 64, for a solid circle. For a hollow circle, moment of inertia is given by mi of the bigger circle minus mi of the smaller circle, which is given by this. And distance of the farthest fiber here also from neutral axis, it is symmetrical, it is same. So y max is capital D by 2. So if you use the formula, that is equal to INA by y max, this is the INA divided by y max, this is the expression you are going to get, or Z. Next, in beams, in addition to rectangular, circular, we are going to have T section and I sections also. Suppose if it is a T section, one important thing here is, it is not fully symmetrical. It is symmetrical about vertical axis, but it is not symmetrical about horizontal axis. Therefore, you have to locate the centroid using first principles. So, centroid has to be located. So, by taking from any one of the sides. So, suppose if you use this as distance from this bottom edge as y bar. So, then y bar is given by, to locate centroid, we have to use this formula sigma ai yi divided by sigma ai. This you have learned in your mechanics, location of centroid of composite sections. So here this is one rectangle, this is another rectangle. So areas we have to find out. We have to locate centroids of these rectangles separately. Those distances are y1 and y2, and if you substitute this formula, you get y bar. So in this case, you can observe that this length will be more than this one, because the area is more concentrated here on the top of the flange of this section, that is the flange portion. So your centroid always it lies in the region where area is more, or area is concentrated. So that's why here this is not a symmetrical section about x-axis. So y max is this one, y1 is y max. So this value you have to take. You have to calculate this. All these value will be given, width, depth, everything will be given. You have to compute y bar, and then you have to calculate moment of inertia also using parallel axis theorem, and then divide it by y max, we are going to get the z value. Of course, this how to find moment of inertia, how to locate the centroid, when I take up a problem, we will explain. So this is for T section, and similar procedure is used for I section also. Now we will take what do you mean by moment carrying capacity of the section. Moment carrying capacity of section is the same as moment of resistance of the section. So this is another word, moment of resistance. So please learn these wordings. So all these words mean the same. So moment of resistance or moment carrying capacity section, as you know, here m is equal to z into f max, that I have used here. So z into f max is m, where z is once again bd square by 6 for rectangular section. Here I have taken an example of a rectangular section. So for a rectangular section, so you have the moment carrying capacity as f max into bd square by 6. So b and d you will be knowing, and normally they will give the value of maximum shear, maximum stress, bending stress also. So f max also you will be knowing. By knowing f max, maybe they may give 50 Newton per meter square, 100 Newton per meter square, like that. M can be found out. So this m you are going to get in Newton millimeter, then you can convert that into kilonewton meter, because normally loads and distances will be in kilonewton and meter. So that is how we can find out. Now another thing is, another type of problem, they will give the value of maximum bending stress, they will give the section B and D, they will give, and they will give the span of the beam also. Now suppose if this particular section is given, is adapted for this beam of some length L, what is the safe load that can be applied on the beam? So this is another type of problem they can ask. That load can be either concentrated load or it can be UDM. In this example, I have taken concentrated load acting at the center, simply supported beam. So AB is the simply supported beam, C is the midpoint where the concentrated load is acting. So equating this moment of resistance, whatever we have got, to the maximum bending moment. So you should be knowing where the maximum bending moment occurs. Here, maximum bending moment occurs in this case at point C only, M max, and its expression is WL by 4. This you should be knowing. So this we have learnt in bending moment shear force chapter. So when a simply supported beam is subjected to central concentrated load, maximum bending moment occurs at the center of the beam, and its value is WL by 4, where W is the value of that load, magnitude of that load, and L is the span of the beam. When you equate this maximum bending moment to the moment of resistance, safe load can be found out. Safe load means the W. W is the normally W is the unknown, so they will give L. So in this expression, maximum bending moment is WL by 4. That will be equated to this moment of resistance, which is F max into BD square by 6. So here everything is known except W. So you can find out the W by equating these two things. Similarly, if you have a UDM on the same synthesis-supported beam, if you are asked to calculate what is the safe UDL that can be applied, small w per unit length, what is the safe UDL that can be applied on the beam so that it is safe. So W is unknown. So here also we know that maximum bending moment occurs at the midpoint. So MC is M max here also. And the expression for maximum bending moment in this case is WL square by 8. So you should remember this. WL square by 8 is the maximum bending moment in the case of UDL. Now equate these two things, that is WL square by 8 should be equated to same F max into BD square by 6. So this BD square by 6 I have written assuming the section as rectangular. If they give T section or I section, you have to take the corresponding values there. Okay, so this Z expression will be different for T section and I section. This I have taken for rectangular section. Now equating these two, this W can be found out. All the other things you will be knowing. So this is how we can compute a safe load that can be applied on a particular beam to take care of the maximum bending stress whatever is given, and for a given particular section. So section is given, maximum stress value is given, span is given. What is the safe load that can be applied on the beam, whether it is concentrated load or UDL, that can be found out using this procedure.